Hi everyone, thank you for watching and thank you for joining me in today's session. I will be talking to you about graphic kinematics for the case of cantilever beams. Starting from Maxwell and Rankine and their approach to graphic statics based on polyhedral projections to construct form and force diagrams. More recent developments advanced the duality of form and force in higher dimensional polyhedral with the construction of the Corsican sum and the trivial shifting of geometry pieces with Clifford algebra. A further dissolution of volume gave its way to the implementation of polygonal faces or loops for describing the stress resultants of a structure and provide a full description. Now, the implementation of the full description into a design methodology with the introduction of an architectural hypothesis by means of designated load paths for the loops is a more recent development. In principle, each loop is treated as a cantilever with a funicular shape at the bottom, like here. And it follows the orientation of the external force by being shifted in such a way that its moving vector's exterior product aligns with the sense and direction of the force. By then selecting a point O along the loop, the distances between that and the loop's discontinuities construct the exterior products of moments at the loop's vertices. The moments are then rotated or projected along the loop segments to create the bending moment diagram, and the torsion values are also translated into a circular graph to make the understanding of torsion more intuitive. The complete diagram on the right visualizes the shear force along the loop together with the bending moment and torsion diagram. It is this cantilever loop methodology that provides the framework to further study kinematics as presented in this paper. Once again, the superimposition of loops leads to a final diagram of bending moments in this case. Applying the conjugated beam method to the full description, a set of three loops is created following the three loads on a given cantilever beam. The superimposition results in the final bending moment diagram that is then used as a new loading diagram. By swapping the boundary conditions as per the conjugated beam method, a new set of loops leads to another bending moment diagram that now shows the deflections. Combining the two methods is of benefit since it simplifies the boundary conditions reconfiguration of the conjugated beam method to a simple swapping from a free end to a fixed end. Further superimpositions can lead to deflection diagrams for more complex structures. At the same time, the combining of the two approaches can be made for the case of non-parallel loads on parallel planes. Briefly showing the moment area method, the angle of deflection at each loading point equals to the area of the bending moment diagram at that point. Of course, same applies for the case of non-parallel loads on parallel planes. Clearly the area and the surface loses its planarity, however the intuitive aspect is of value. Moving to the principle of virtual work, the top row shows the construction of volumes equal to the deflections. The exterior products of virtual loads multiplied by the distance from the support creates the closed shapes together with the existing bending moment diagram. At the same time, by replacing the virtual loads with the original forces at the bottom row, the volume values are equal to the real internal work. The process provides a visual manifestation of the principle of virtual work. Of course, this can be applied to non-parallel loading on parallel planes. the intuitive aspect of this geometric method is of benefit despite the non-planarity of the volume faces. Finally, a simple 90-degree rotation of the initial bending moment diagram here constructs a shape whose volume represents the total external work. The value is equal to the individual sums of the total internal work upon 2, but most importantly, they are the same sum of volumes as the original shear force diagrams extruded along the direction vectors at the center. Clearly, the same can be applied to non-parallel loads on parallel planes. To conclude, given that the deflections can be extracted from the conjugated beam method in a more linear fashion using the loop method, as shown, the application of the full description and the orchestration of the loop methodology proves again to be of great benefit not only for graphic statics but also for graphic kinematics. Furthermore, the implementation of vector products for constructing volumes in the study of kinematics is of value in order to visually grasp the principle of virtual work. Given the significance of vectors in computer-aided design applications, the methods discussed here can lead to fruitful directions. Thank you.